Rightio, hello students, welcome to today's lesson on allocation problems. So today we want you to be able to use a bipartite graph in its tabular or matrix form to represent an assignment or allocation problem. We'll also have a look at the optimum assignments for small scale problems by inspection. We'll use the Hungarian algorithm for larger problems. So let's pretend we've got three boys here, Ryan, Malachi and Joshua, and they've got a group project and they've got to create a poster. And if we have a look here, they've got time that they can perform each job listed in this table below. We want to use this to calculate the minimum time by inspection first of all. So we can see there's three jobs: researching at the library, buying stuff at the shops and annotating the poster. Now Ryan will take 200 minutes for research, but is a gun at shopping and not so fun at annotating as well. So Malachi, he's researching, takes 120 minutes. Buying stuff will take him 80 minutes, but annotating the poster will take him a bit quicker. Josh, it'll take him 150 minutes to research at the library, 70 minutes to buy stuff at the shops, and 110 minutes to annotate the poster. So how can we use this now to get this job done the most efficiently? So what we're going to do is just put this in matrix form, and then we're going to allocate each person a job. Now we've got two real options here. We can see that just looking down that I've highlighted there in yellow, the quickest possible times, just making sure each person has one job. It's pretty definite that Ryan's going shopping. Now we're going to just compare the options. Well, the first option will take 270 minutes and the second option will take 290 minutes. So we can say, well, the minimum time is 270 minutes. Convert that to hours. Well, 6 4s are 24, so that's 4 hours and 30 minutes, or 4.5 hours. It can be achieved by assigning the library to Malachi, the shopping to Ryan, and the poster work to Joshua. Now I can also use the Hungarian algorithm for such a problem. So I've just put the matrix up there in the top right hand corner. We're going to do what's called a row reduction first of all. And what that is where you perform when you perform a row reduction, you're just going to subtract the minimum value in the row from the rest of the row. So if we have a look here, here's our minimum value, here's a minimum value, and here's a minimum value. And we're just going to perform that row reduction until we've got a line of zeros. So you can see that there. Now we're going to do a similar thing, but we're going to do a column reduction. So we're just going to say, well, what's our minimum value? Well, this now looks like a minimum value. Well, 0 is the minimum value there, and 20 is the minimum value there. So let's do our column reduction. And so what have we done? We're ending up now with a line of zeros in both column and row form. So what we want to do is determine the minimum number of horizontal and vertical lines that are required to cover the zeros. Now, if you can cover the zeros with fewer lines than there are columns, you circle the smallest uncovered value. And that's going to be this one, hasn't it? So now that we do that, we're going to subtract that minimum uncovered number, that 20, and add it to the intersection. So that's got to be added there. So what we're going to do is make it look a bit like this. So you can see that I've taken 20 from all the values but added 20 to the intersection there. Now I've just drawn that as a bipartite graph connecting the people with the jobs based on the zeros. So what I can see here is what that's a 0, that's a 0, that's a 0, that's a 0. We've got Ryan, Malachi and Joshua, and we've got the library, we've got shopping, and we've got poster work. So I can connect Malachi with the library, so that's that line, and then I can connect Ryan with shopping, so that's that line there. I can also connect Malachi with a poster, so I can do that there. And then let's look at Joshua. Joshua can be connected to the shops, and then he can also be connected to the poster work. Now we're going to allocate jobs based on the zeros or the edges with the degree vertex of 1. So, well, that's obviously got 1 there, so that's telling me Malachi to the library. This one here, that's telling me Ryan to the shops. And that leaves Josh to do the poster. So the Hungarian algorithm only works for square matrices. And we've got a summary here. So what we do is we have our matrix at the start, and then you perform a row reduction, then do a column reduction. You cover the zeros with the minimum number of horizontal or vertical line segments. And now, does the number of line segments equal the number of rows? If yes, you can allocate based on zeros. If not, you've got to circle that minimum number and then add the minimum uncovered number to the values under the intersections of the line segments and subtract that minimum uncovered number from uncovered values. And we're going to leave those other values unchanged. Now, sometimes we want to maximize, and to do that we're going to have to create complementary matrices. So in order to determine an overall maximum of an overall quantity, for example income or scores, you're going to create a complementary matrix before proceeding with the Hungarian algorithm. So for complementary matrix, you just replace each element with the matrix with the largest number in the matrix minus the element value. So it kind of looks like this. Oops, I didn't animate. So step 1, we can see that here's our starting off matrix. And we're going to create a complementary matrix by subtracting each element from the maximum element. So let's highlight our maximum elements, and I've got 4 of them. They're all the same, so that's 7. So just saying every element taken away from the maximum. So it looks a bit like this. So 7 take 5, well that's going to give you 2. 7 take 7, well that'll give you 0. 7 take 5 will give you 2, and 7 take 5 will give you 2, and so on. Okay, so we perform a row reduction and perform a column reduction. In this case, we don't need to do a row reduction or a column reduction because there's a 0 in every row and column. Then we're going to assign tasks based on those zeros. So here's these tasks, and we're just going to put them in the original matrix. And we can now just determine the maximum value of this complementary matrix from the complementary matrix, and the maximum value of this allocation matrix is going to be 28. Are you able to use a bipartite graph and its tabular matrix form to represent an assignment? And can you also determine the optimum assignments for small scales, problems by inspection, or by use of the Hungarian algorithm for these larger problems? If you can, work on these mastery exercises to prove it. Good on you.